Okay, let's get started. So, hello everyone. My name is Lokesh Kumar Lal, and today I am presenting my project on predictive network congestion. And this is something that comes in from my experience as I work on the service provider networks. And to start with, on the massive internet routing platforms, we currently detect congestion reactively, which is the problem. So by the time an interface hits 90% utilization, the packet loss has already started, impacting global traffic. And the problem is complex enough, which makes the machine learning an opportunity to kind of, influence these global traffic trends. And at the same time, we process billions of telemetry points per minute via SNMP or gRPC. So it's again a great value add, and there's also economic value, with proactive detection on the backbone networks. It helps the with the SLA penalties, which is huge, and also kind of ensures internet stability. So that's the opportunity. Now, our goal is to provide a 30 to 60 minute, lead time for network operators, which is good enough, for success. Our outcome metric is a reduction in congestion related tickets across the backbone, and our output matrix focuses on recall because missing a backbone congestion event is catastrophic. And precision to ensure that our NOC engineers aren't overwhelmed with false alarms is, it's imperative as well. So what we'll do is we'll analyze factors like the interface throughput, which is the internet interface on a router, essentially how these routers send traffic to our homes. We look into the BGP peering states, which is a routing protocol, as well as the global traffic trends. Now, my solution is an ML-driven dashboard that predicts congestion probability per routing node, and I have a great demo as well. To validate this, we'll start with offloading the offline backtesting on historical internet traffic logs. And then we move to the silent mode, where the model generates, these kind of shadow alerts on live internet routing platforms. And we'll compare these alerts against the actual traffic spikes to kind of tune it, get this fine-tuned. And finally, we run a controlled pilot on a specific edge peering region to measure how reactive outages are prevented by proactive rerouting. So now to demonstrate this, this is a predictive traffic dashboard that I've created, and this is the interface for our internet routing platforms, the routers itself. And instead of a simple alarm that triggers after a failure, our model provides a probability score as well as a predictive lead time. So which, kind of helps with the overall accuracy. And on right, the right-hand side, the forecast graph shows our predicted traffic crossing 90% capacity threshold well before it actually happens. So this UI allows a network engineer to hit the initiate proactive reroute button and shift traffic to an alternate route, preventing an outage. Now, from the system architecture perspective, we have got few metrics. So first is the cloud versus the edge. So here the training happens in the cloud for the massive data aggregated across the network, while the interface is pushed towards the edge, which is the internet edge for real-time alerting. And then you have the offline versus online training. So this is, more like the offline training with weekly updates for, gradual shifts in internet usage. And then you have, lastly, the batch versus online prediction. So now predictions must be online because internet traffic moves at a light speed, and the model must process streaming telemetry in real time to provide these actionable, 30 to 50 minutes morning. Now, to conclude, we must, manage the risk like data drift, where new AI workloads or streaming services change the overall global traffic profile, and the concept drift, where a hardware upgrade on a routing platform, really changes the behavior. So by maintaining the human in the loop for critical rerouting, we kind of ensure that we don't we kind of get into these problems. So that's been my time. Thank you so much.